Next up is Yanan Zhao, PhD student at the University of Wisconsin-Milwaukee, presenting in person.
Good morning, everyone. I'm Yanan. I'm a PhD student from Civil and Environmental Engineering, UW Milwaukee, and my advisor is Yingwang and Xiangping Xu. Today, my topic is about the PFAS in groundwater adsorption to the aquifer material. And I think PFAS is a hot topic. I don't want to talk too much about the basic knowledge. What is PFAS? It's a kind of synthetic organic chemical. We use PFAS from 1950s, I think. Yeah, it's a long time, and now it's spread everywhere and cause a lot of problem. And from last summer, EWD gave a map about the PFAS contamination reported in the drinking water source. Only for the drinking water source, we can see there's so many spots. That's where there's PFAS contamination reported. And as I focus on the PFAS contamination in Wisconsin, so I also got the PFAS contamination information from the DNR website of Wisconsin. And the contamination there is not too bad, but also not good. And according to the PFAS contamination sites and the major aquifer material type in Wisconsin, we selected 5 points to collect some aquifer material and do the research. And the point 1 in that map is a quarry. As during our research, we found dolomite was a very important mineral in the aquifer material that have a relationship with the PFAS adsorption. So we need some dolomite-rich sample to do the research, but dolomite is difficult to synthesize. That's why we need to find a natural dolomite-rich sample. So we use a dolomite rock. And after I got the dolomite rock, I grind into granular, and then all the pre-treatment of the that one is use the same way with other aquifer material. Before I use the material for the experiments, I cleaned them to avoid the possible PFAS background. We collected the material from nature. There may some PFAS contamination. So before that, I need to clean it first. And the material characterization results show that in our material, the dolomite and the quartz are the main minerals in the material. And from the SRD result, we can see the characteristic peak of the quartz and the dolomite. And from FTIR, we can also see the peak, which produced by the carbonate and silica oxygen bond. That makes sense with the result of XRD. And also from EDS mapping, we can see the magnesium, the calcium, or the silica are the main elemental in our material. That also makes sense with the characterization of the result of XRD and FTIR. And other parameters I listed in the table. From here, I want you to pay attention to the dolomite content in our aquifer material. From AM1, aquifer material 1 to AM6, the dolomite content decreased. Usually, I call the AM1 is dolomite-rich sample, and AM6 is a sand-rich sample. As the AM6, they're almost 89% sand. That's why I call it sand-rich sample. I think that's all we need to know about the material. About the PFAS adsorption experiments, I use batch experiments, and I use mixture of 6 PFAS. The parameter of the PFAS I listed in the table, please pay attention to the DOW. And in that order of PFAS, the DOW increased. DOW is a very important parameter in our research. And I use the concentration, the PFAS concentration in my research is from 100 nanograms per liter to 5 nanogram per liter is more relevant to the environmental concentration. And I use groundwater, had a pH of 8.5. The contact time is 7 days. After that, I use LC mass to detect the PFAS concentration in the liquid part. Well, our adsorption result, and I use different models to fit the result, but our result fit the friendly model and the linear isotherm model very well. Let's see the function of the friendly model. There is a parameter n called the friendly exponential factor, the n. Kf, both Kf and Kd, both Kf in the friendly model and Kd in the linear model, you can thought it's a consistent. So when the the factor n in the friendly model is equal to 1, we can find the function of friendly model is equal to the function of the linear model. I give all the parameters I calculate, use the friendly model, use our own data, the result data. The n, we can see from our experiments, in the most case, the parameter n is close to 1. That also explains why our result can fit both the friendly model and the linear model very well. As just now we said, when the n is equal to 1, that two models are the same. As both the friendly model and the linear model works well, and the linear model is more easier. So during my research, I used the linear model to calculate KD. Well, KD is solid water partition coefficient. Here we can understand KD as a adsorption affinity. When the KD is higher, it means the PFAS is preferred to adsorbed by the aquifer material or by solid. And the picture from picture A to picture F present the aquifer material 1 to aquifer material 6, and different color of the line with the different PFAS. For the same PFAS here, let's see the orange line for the same PFAS from aquifer material 1 to aquifer material 6. So we can see the slope of the line become lower and lower. It means the slope is the KD, as the x is QE is CE and the y-axis is QE here in the picture. And when the slope becomes lower, it means the KD become lower, become smaller. And just now we said from AM1 to AM6, the dolomite content decreased. Now we can get that when the dolomite in the aquifer material decreased, the KD decreased. And for a given material, we can just now, I said, please pay attention to the log DOW of different PFAS. And here, I can see the conclusion. When the DOW increased, the KD increased for a given material. And that result is consistent with the previous study that the PFAS adsorption onto soil, onto sediment, and maybe other minerals is the same. To figure out the main factor that affect the PFAS adsorption onto the aquifer material, we also do a PC analysis, and from the result we can say the log DOW and the dolomite content has a positive relationship with the log KD. And they are the two main factors that affect PFAS adsorption onto the aquifer material. Just now we said they have they have a relationship with the KD. Now we know they have positive relationship, but the positive relationship is linear or nonlinear. Until now we don't know. I'll show you. To figure out is linear or nonlinear. So I plot the log DOW and the log KD, and log the dolomite content and the log KD in the map in the bioplot, we can say for the same PFAS, they have the log DOW have a linear positive relationship with the dolomite content for the same PFAS. And also for same PFAS, the log KD have a linear positive relationship with log DOW. And it's very interesting. Let's use the first map, for you, the left one. The intercept of different fit lines have different intercept. When I check what in fact the intercept I find, it's also interesting. The intercept has a positive relationship with that one, the dolomite content with log KD. The intercept has a positive relationship with log DOW. And for the other one, the log DOW with log KD, the intercept has positive relationship with dolomite content. As dolomite content and log DOW are the main factors that affect PFAS adsorbed onto the aquifer material, and both of them have the linear relationship with log KD. So we created a multilinear regression model to estimate the log KD for a given PFAS adsorption onto the aquifer material which contain dolomite. Of course, which contain dolomite, as there's a very important parameter called dolomite content. And the data, our experiment data fit the model very well. The R square is more than 0.9. And from the picture, you can also see all the points fall in close to the line, the dash line. The dash line is 1-to-1 line. It shows that the model can use to estimate the log KD of PFAS adsorption on the aquifer material that contain dolomite. And when use that model, we can get KD. We can get log KD. When we got log KD, it's easier for us to get KD. For a given material, when we get KD, and it's easy for us to know the bulk density and the porosity for a given material. And also we know KD, so it's easier for us to use that function to calculate the retardation factor. And the retardation factor in our research listed in the table, it also has positive relationship with the dolomite content and the log DOW. When you know the retardation factor, we can use the 1D transport model to calculate the transport distance, the transport time, and even the concentration at a specific time and distance. And for easier to compare, I use the half source concentration here to compare, and we found the compared to AM6. Just now we said it's sand-rich material. Compared to the sand-rich material, the transport distance of AM1 is dolomite-rich material. The transport of AM1, the PFAS transport distance in AM1 can reduce about 4 to 10 times. It's a lot. And as the dolomite is abundant in the environment, and it has a large adsorption affinity, and it already for a long time. So we think it's the time for all of us to pay attention to the dolomite. I think that's what we got now. Well, thanks for my advisor, my lab mate, and thanks they are to support this research. And thanks for all of you to listening. And I leave our email here if you want more details, or if you have questions later, maybe you can send us email. Thank you.